there's something off about 3E Atlas. Toward the end of July, leading space observatories like Hubble and JWST collected amazing data on this unique interstellar comet. But right when its coma swelled beyond 300,000 kilometers and news of a green hue and unusual brightening surfaced, official updates ceased. NASA pointed to solar geometry and its safety protocols. Yet this sudden quiet is noticeable as Oumuamua and Borisov triggered waves of quick updates. This lack of information is doing more than just sparking strange theories. A failure to provide timely answers might erode public confidence in the process of revealing cosmic finds. So what is the actual cause for the silence? And what aren't we being told about 3E Atlas? The Hubble Space Telescope targeted 3E Atlas on July 21, 2025, and snagged the clearest pictures ever of this interstellar guest. On August 7th, roughly 2.5 weeks after those pictures were released, revealing a nucleus not exceeding 5.6 kilometers wide and a massive dust plume extending toward the sun. By August 6th, the JWST had its chance employing the NIR SPEC instrument to collect spectra. However, for Webb, the public only received technical notes and initial observations. There were no major images, only clues that analysis had begun. On August 27th, Gemini South also participated, taking pictures that verified the comet's activity and developing tail. That information showed up in the public archive on September 4th and 5th, offering scientists and hobbyists a new view of the expanding coma and changing dust patterns. Every release sparked a wave of online chatter, though the time between them began to grow. Following September 22nd, the rhythm shifted. There were no new major images or recent data from Hubble, JWST, or Gemini. The stream of official news slowed down dramatically. For anybody following the comet's journey, the gap was undeniable. The public release schedule, once consistent, now revealed an expanding void. The real question became not what was observed, but why the updates stopped. Aiming Hubble or JWST at 3I Atlas is more complex than just pointing and clicking. Both observatories operate under firm solar avoidance regulations, technical limits designed to shield their delicate optics and sensors from wayward solar rays. With Hubble, the guideline is straightforward: no observing inside a 50-degree radius of the sun. JWST, with its enormous sun shield and sensitive infrared instruments, is more restrictive, requiring at least an 85-degree separation. These angles are non-negotiable. They are hard-coded into the system. Should a target wander too near the sun's location, the software blocks all efforts to plan or run an observation. This danger isn't merely hypothetical. Direct solar rays could cause instruments to overheat, irreversibly harm detectors, or potentially jeopardize the whole mission. As 3E Atlas traveled on its course, its solar elongation, the angle connecting the comet Earth and Sun, decreased daily. By the end of August, it had drifted beyond Hubble's 50-degree boundary. Shortly after JWST's NIR SPEC observation on August 6th, the comet passed JWST's 85-degree limit. From that moment, both observatories went into a mandatory blackout period. The scientific teams at the Space Telescope Science Institute, responsible for scheduling and operations, could only stand by. These keep-out zones are built directly into the mission's planning software. Any attempts to bypass them would set off automatic safing procedures and might stop all science operations pending a complete review. This isn't a matter of bureaucratic hesitance. These are fixed physical constraints. Not even urgent target of opportunity proposals can get around the keep-out zones. The sole option is to wait for a change in geometry. For 3E Atlas, that means no new flagship data until its elongation increases. Orbital calculations suggest this will occur in early December. For now, the blackout continues and the premier observatories stay silent, not out of choice, but due to their design. Clues about the true nature of 3E Atlas started emerging right after the initial science data was released. Hubble's images from July showed more than a dust tail. They revealed a massive coma, a gaseous and dusty envelope extending almost 348,000 kilometers across. That size is over a quarter of the sun's diameter and significantly larger than most comets at that range. The most fascinating clue emerged from early spectroscopic data. Astronomers began murmuring about a remarkably strong carbon dioxide signature in the coma. It's critical to note that by late September, nobody had published a peer-reviewed spectrum that confirmed carbon dioxide's dominance, but the signs are there, and the science teams have not refuted it. For any comet visiting the inner solar system for its first time, this would be a significant chemical hint. The majority of local comets are water-rich in this region. Along with the official data, amateur astronomers kept up with their own viewings. A few of them reported a noticeable greenish color in the coma, probably from dicarbon or cyanogen, typical signatures in comet chemistry but with a slight variation. Some sky watchers pointed out the greens seem brighter and more enduring than in standard comets. However, without complete spectral information, identifying the cause is difficult. The sunward plume initially seen by Hubble and later Gemini also sparked discussion. Its form and luminosity appeared to change nightly, triggering arguments over whether surface eruptions or viewing angles were the cause. Photometry, which tracks the comet's brightness, introduced yet another level of uncertainty. Measurements from both amateur and professional sources varied greatly, sometimes by over a full magnitude. Part of that is due to different equipment and calibrations, but some of it could indicate genuine swift changes in the coma or its nucleus. With the main observatories offline, the variability in these ground-based observations became the primary insight into 3E Atlas's behavior. Right now, the strongest available evidence suggests a comet with an enormous coma, a potential carbon dioxide-heavy composition, a sunward plume, and a color that just won't stay consistent. Lacking new flagship data, every strange detail fuels speculation and serves as a reminder of our reliance on the small stream of amateur and ground-based findings. By the end of September, the quiet surrounding 3I Atlas felt more than just technical. It became personal for the observers on the ground. Social media was flooded with frustrated and speculative posts. One amateur astronomer posted, "This is like hunting a phantom. We're guessing what's really going on out there every night." Another posted, "Why can't we access the raw data? What is the holdup?" The reality is that the journey from telescope to public access is far from immediate. All observations from Hubble or JWST go into a holding pattern. Once the data is received, it undergoes calibration, cosmic ray removal adjustments for detector anomalies and the subtraction of background noise. For JWST, the procedure is more complex. Each NIR spectrum is run through several software stages as instrument teams scan for artifacts or calibration mistakes. A single overlooked error could lead to claiming a chemical signature that doesn't actually exist. On top of the technical challenges, there is also policy. Both Hubble and JWST have proprietary periods. This is 6 months for the majority of Hubble programs and up to a year for JWST. The principal investigators' PIs get the first opportunity with the data, a custom design to compensate those who created and secured the observing proposals. While some PIs decide to make data public sooner, a lot of them wait until their groups have checked and double-checked every single pixel. This is particularly true for high-interest targets like 3I Atlas, where a hasty claim might send shockwaves through science and the media. Standard institutional procedures add even more complexity. Each press statement or major image is reviewed by several agencies, NASA, ESA, and sometimes the CSA for JWST. Every group examines the results, verifies legal and contractual compliance, and agrees on the release timing. Even an uncontroversial dataset might be stuck for weeks in this review process awaiting approval from various project scientists and communication managers. For 3E Atlas, this procedure was even slower as teams considered the dangers of publishing incomplete or unclear findings. As a JWST co-investigator noted, it is better to be correct later than incorrect quickly. With any interstellar object, you don't get a second look. This all means that while the public is eager for news, official sources proceed at their own speed. That feeling of anticipation of looking at old images while theories circulate is inherent to the system. To many in the community, this information void is like a barrier. For the mission planners and data specialists, it's a barrier built for precision, not for concealment. Yet the longer this quiet persists, the more it influences the narrative, transforming procedural holdups into speculative fuel and standard caution into a cause for concern. The rumors about 3E Atlas began to escalate as soon as the major telescopes went dark. Some theories attributed the blackout to secret sensors, implying that military or spy satellites had captured images the public would be denied. Others focused on preventing panic, the notion that agencies were controlling the narrative, withholding information to prevent sensational headlines about an interstellar oddity. A different group even asserts the data is just too bizarre for a quick release, that scientists are working frantically to understand something that doesn't conform to the standard model. The current media environment just adds to the fire. Reports on comets such as Lemon or Swan, bright, simple to see, and photogenic, tend to dominate social media feeds and news headlines. Their high visibility makes them perfect for algorithms. What you can see tonight is a guaranteed click winner. Conversely, 3E Atlas, with its irregular updates and technical challenges, is disappearing from trending topics. When there's no new information to present, the void is filled with conjecture. After the Gemini South images were released in early September, social media activity for 3I Atlas surged to 10 times that of normal comets, then skewed toward conspiracy theories as the data drought continued. However, the behind-the-scenes truth is much less sensational and far more systematic. Every single observation from Hubble or JWST goes through a multi-phase pipeline before anyone outside the science team sees it. To start, the raw data is downloaded and paired with spacecraft telemetry. Then the calibration processes start. Cosmic rays are removed, detector anomalies are fixed, and background noise is subtracted. With JWST, this involves navigating at least 3 primary phases: detector level adjustments, instrument calibration, and sophisticated processing like co-addition and artifact removal. Each phase is inspected for errors, marked for oddities, and occasionally reprocessed if something seems unusual. Once the data is considered science-ready, the principal investigators examine it, typically under a proprietary hold, 6 months for Hubble, up to a full year for JWST. Only when the PI and their team are certain about the findings do they proceed to the subsequent stage agency review. NASA, ESA, and at times CSA all provide input, checking for any legal, contractual, and scientific conflicts. Press officers schedule the release dates, occasionally holding off for weeks until everyone gives their approval. If the results are inconclusive or suggest something unforeseen, the procedure slows down even more. A premature announcement, particularly for a major target like 3I Atlas, could lead to a public correction or even a complete retraction. The difference from previous interstellar encounters is stark. When Oumuamua was spotted in 2017, the data flowed out nearly in real time. Preprints, public discussions, and even wild theories flooded the internet within just a few days. Borisov, 2 years after, maintained a predictable textbook pace. Images and spectra were released on schedule without much fuss. For 3E Atlas, the mix of technical difficulties, careful review, and multi-agency approval has resulted in a slow and inconsistent flow of information. This creates a perfect environment for rumors and agitation, yet under all that noise, the pipeline advances one step at a time. Every stage is intended to spot errors before they are made public. For the engineers and scientists involved in this process, it's not about hiding anything or managing a story. It's about ensuring the science is accurate, even if it takes longer than anyone desires. The Mars flyby on October 3rd presents the next major chance for new information on 3I Atlas. At its nearest point, the comet will be just 0.19 astronomical units away from Mars, or about 28 million km. That is relatively close in space terms, but it's still well beyond the range of any high-definition imaging systems. The ExoMars Trace Gas Orbiter, or TGO, has the KSIS camera, which is frequently praised for its detailed 5-meter per pixel photos of the Martian landscape. But from this range, KSIS encounters significant physical constraints. In the best-case scenario, one pixel would span over 300 kilometers. The nucleus of 3I Atlas, measuring between 320 mm and 5.6 km, will appear as just a single blurry dot. No discernible detail, no distinct shape, just a dim spot of light set against the starry expanse. HiRISE on the Mars Reconnaissance Orbiter, with its wider aperture, can perform slightly better down to roughly 34 km per pixel, but that is still far too coarse to resolve the nucleus or any features in the coma or tail. These instruments were designed to map Mars from a close distance, not for observing deep space objects moving through the sky. Following a comet at such interplanetary velocities isn't part of their programming. Exposure times must remain short to prevent blurring, and the signal-to-noise ratio diminishes quickly as the comet moves further away. So what information can Mars orbiters truly provide? They offer photometry, a way to measure the comet's brightness when Earth-based and flagship telescopes are blocked by solar geometry. A point source detection from Mars orbit is incredibly useful for monitoring the comet's location and activity, particularly if any sudden flare-up or change in brightness occurs during the flyby. The data processing pipeline is efficient. TGO and Mars Express are able to download and handle these observations in just a day or two, assuming no technical issues arise. But for anyone anticipating a stunning close-up image, it is crucial to manage expectations right now. The Mars flyby is focused on timing, not on fine details. Its actual importance is in providing coverage during a period when all other observatories are forced to avert their gaze. Perihelion for 3 Atlas occurs on October 29th or 30th as the comet passes approximately 1.36 astronomical units from the Sun. At this range, it isn't considered a classic sun grazer, but the intense heating and high speed will still place the nucleus under considerable strain. So what should we be looking for as the comet travels through its solar passage and comes back into view in December? First, pay attention to the light curve. Abrupt increases in brightness, particularly sharp and brief spikes, could indicate surface fracturing or outbursts. However, a steady rise and fall that matches the expected curve as the comet approaches and then moves away from the Sun suggests a consistent release of volatiles instead of a breakup. It's important to remember, one brightness spike doesn't confirm fragmentation. You need to observe a distinct pattern, preferably one that is verified by several different observers. Next, watch for any alterations in the antitail, the sunward-facing spike visible in wide-angle photos. As Earth's vantage point changes in relation to the comet's orbital plane, the antitail might seem to flip or disappear. For 3E Atlas, the antitail's visibility should be at its highest, near perihelion, then quickly fade as the geometry shifts into December. Monitoring its orientation across different images is a very effective method for verifying orbital characteristics and dust dynamics. The color is also important. If the greenish color reported by amateurs vanishes or changes after perihelion, it might signal the depletion of certain molecules as surface ices are used up or new material gets exposed. But only spectra can truly confirm what is actually happening. Images by themselves can be deceiving. In December, as the comet's elongation grows and the major telescopes can observe it again, we should anticipate a fresh wave of high-definition imaging and spectroscopy. And looking further to 2026, a well-positioned Jupiter might provide another chance for observation if 3E Atlas makes it through its solar passage intact. For the time being, the most valuable tool is a discerning eye. Compare photos from different dates, double-check photometry readings, challenge sensational claims, and keep in mind that color is not chemistry without spectra. The entire global community, from professionals to amateur observers, is monitoring this together. The saga is not finished, it's simply turning to a new chapter. Official reports cite technical limitations, Hubble's 50 degrees and JWST's 85 degrees solar avoidance zones, plus multi-week data processing and firm proprietary restrictions. Despite these reasons, the lack of immediate updates on an interstellar body with a CO2-rich coma, sunward plume, and reports of a green color has left significant scientific questions unanswered. No peer-reviewed spectra confirming the chemistry of the coma have been released, and the full meaning of the brightness variations remains unexamined. As Mars orbiters get ready for a close approach at 0.19 astronomical units, the upcoming images and spectra, with their 24 to 48-hour download times, could at last resolve the information jam. Until that happens, the 3i Atlas situation demonstrates how institutional prudence and technical constraints can dictate what the public gets to see and not see regarding the most infrequent visitors to our solar system.